Hi, this is Jemin Chang from Team Hydra giving our final project report for our NLP semester project. Our task was to create two programs, an Ask program, which takes a Wikipedia article and a number of questions as input and generates that number of intelligent questions about the article, and an Answer program, which takes a Wikipedia article and a list of questions and answers those questions correctly and fluently. In implementing our system, the biggest assigned decision to make was the decision to not try to use semantics. The reason for this is that semantics is a young field and it's just extremely difficult to try and model meaning in a way that allows us to ask and answer questions. Instead, we rely on syntactic structures, manipulating and transforming them in order to answer questions and ask questions. In this, we relied heavily on the Stanford parser, which we use through an NLTK interface to parse our sentences as strings into parse trees. This imposes some limitations due to the computational intensity of parsing, and we had to limit sentence length and the number of sentences we were parsing in order to work within the time limits and make sure that our parser didn't run out of memory. Here's how our Ask program works. It takes as input a Wikipedia article and a number of questions. We parse the article's HTML using Beautiful Soup, and we separate the sentences using NLTK's sentence segmenter. In this list of sentences, we want to look for simple predicate sentences. These represent facts which we can then transform into questions about the article. Simple predicates should be an NP, VP, followed by a period, which are all the children of a sentence. This sentence should also be the child of a root node. It's important that we have this root context because we want to find full sentences in the article, which are predicates, not sentences that may be complements of complementizer phrases or relative clauses which may not represent actual facts that we can then transform into valid questions. We also look for appositions, NPs separated by commas representing that they are equal in some sense, and we transform these into predicates as well by simply saying NP1 is or are NP2. Now that we have a list of predicate sentences, we can transform them into three types of questions. First, binary questions. These are simple yes-no questions, and the process for transforming them is quite simple in English. We invert the positions of the subject and the auxiliary verb. If there is no auxiliary verb, we insert do, and we conjugate it appropriately using the pattern.en module. We also make confounded binary questions. These are binary questions where we substituted the subject NP with a synonym, sister, a hyponym of a hypernym, or an antonym of the subject, using word-net relations. Lastly, we ask WH questions. We look for specific syntactic structures within the predicates to ask WH questions about. For instance, we look for adverbs to ask how questions about, or NPs to ask what questions about. We also have to use named entity recognition to generate some of these questions. So we use Stanford's NER tagger to named entity tag our sentences so we can identify people NPs, location NPs, and so on. When we identify an appropriate constituent, we remove it from the sentence. We invert the sentence using the same process as for normal binary questions. And we insert the question word at the beginning of the sentence. Importantly, we restrict our attention to the subject, direct object, and indirect object positions of the sentence. Focusing only on these standard positions allows us to reliably create grammatical questions. Because WH movement restrictions on English prohibit extracting noun phrases from relative clauses, for example, and this will result in ungrammatical questions. The last step is to rank our questions. We rank them according to their length, the reliability of certain WH words, and we try to give a good mix of the three types of questions. Now for our answer program. The input is a Wikipedia article and a list of questions. Again, we start by parsing the HTML and separating the sentences. Then for each question, we identify the question type by parsing the question with the Stanford parser and observing the first few labels in the tree. We found that it was quite reliable based on a few key labels to identify whether the question was binary or WH. If we're unable to determine the type of the question, or if it was too long to parse, the best we can do is find the sentence that's closest to the question in the article and print it as the answer. We do this using the cosine similarity of the TF-IDF vectors of the sentence from the article and the question. If we are able to identify the question type, we start by transforming the question back into a declarative sentence using the reverse of the subject-auxiliary inversion process we use in our Ask program and removing a WH word if there is one. The idea here is that this predicate form will more closely resemble the sentence in the article that will give us the answer. Then we identify the closest sentence in the article, again using cosine similarity and TF-IDF. For a binary question, we parse the predicate form of the question and check if all verb, noun, adjective, and adverb heads are present in the sentence we found from the article, or if hyponyms of them are there. If so, we say yes, otherwise we say no. For WH questions, we parse the selected sentence from the article and find constituents in it that match the question word, the same way as they do with the ASK program, but without the restriction of looking only at subject and object positions. For each of these matches, we look at the article from the sentence with the match removed, and compare it to the predicate form of the question with cosine similarity. But we tie-break with the length of the maximum common contiguous string of words between the two. This allows us to capture the gap property of WH questions by identifying the constituent that, when removed, produces the same gap that exists in the predicate form of the question. This allows us to correctly identify Shamir rather than Alan as the correct answer in this case, even though both of them have the same cosine similarity to the predicate question vector. And that's how we implemented our asking and answering systems. Thank you.